2p6, 3s2, and 3p5.
3p3?
Oh, is it? Oh, sorry, yeah, 3. I was counting my s's there. 3p3. You could write it out like that. You could also draw the 1s box, stick your 2 electrons in it. 2s box, stick your 2 electrons in it. All the way down. Someone want to help me out with this 3p? Where am I going to put these electrons?
One in each box.
Pointing up.
All in the same, one in each box,
Pointing up.
all pointing in the same direction, right? So we could use this notation, we could use this notation. There's also a shorthand version of this notation available, and that is that we identify the filled subshells by putting in brackets the name of the noble gas of the last filled subshell. So our n equals 2 subshell is filled, and we have an unfilled n equals 3. And so to indicate that we have a filled n equals 2, we could write in the noble gas neon in brackets, indicating that that subshell is filled, and then simply write 3s2, 3p3. So that notation is legal. I've never seen this notation used with the box notation, but theoretically, it's the same thing. So instead of writing out all of this, we could just write in neon and then draw our 3s and our 3p. You can write it out like that. I'd accept any of these. I'm not absolutely sure that that someone grading your test who isn't me would accept this notation. I would accept that notation, but I can't promise that anyone else would. And a couple of things to note. So I said that you fill your lowest energy orbitals first. And I said that the principal quantum number, so the n equals 0, 1, 2, 3, or whatever like that, indicates the relative energetic positions of those orbitals. There's a slight twist to this. This orbital right here is the 1s orbital. This guy right here is the 2s. 2p. You got your 3s right here. You got your 3p right there. Your 4s shows up here, but it turns out that when you do calculations on the energies of these levels, the 4s levels are slightly less energetic than these orbitals right here, which, based on their radial separation and their symmetries, are called the 3d orbitals. So in your periodic table, your 4s shows up before your 3d orbitals because those 4s orbitals are actually, even though they have a higher principal quantum number, they're actually lower in energy than the d orbitals with principal quantum number 3. Right? And so when you're filling these, once you get to the level n equals 4 level, you're going to put in 2 electrons into your s subshell, and then you're going to start filling d subshells. So you have to remember that with your notation. there are little twists, and I don't remember every single one of them, but I'll give an example of one. I forget which element this is, but let's take a look at a substance that has a filled n equals 3 level. So we got our 3s orbital is filled, our 3p orbital is filled, and now we're filling our 4s and our 3ds. Let's say that we have a situation where we have 11 electrons to fill across this period. So we'll stick an electron in here, electron there, and then a bunch of electrons over here. And you'll notice that I've left this last guy blank. So I've got 2 electrons in my 4s, and I've got 9 electrons in my 3d. There's little twists in chemistry all the time, and it just has to do with energy minimizations of these charges that are distributed, in the volumes. It turns out that having a filled 3d level gives you an extra energy minimization. So nature kind of wants to get that 10th electron in the 3d level. And so what it'll end up doing is it'll pull an electron out of the 4s and they'll throw it into the 3d, just because it's, putting it in that 3d level is actually the lowest energy position available for that electron. And so there's a couple different elements that have kind of anomalous configurations, and it really just has to do with the way that those charges are interacting with each other in space. And so pay attention to that in lecture, when they probably listed a couple of those examples for you of when that happens. But basically it's all energy. It's all nature finding the path of least resistance, the lowest potential spot to stick those electrons in. All right. Okay, so you guys are supposed to, you've got some questions to answer in your protocol for this thing, experiment number 2, in your workshop manual, and then I'm supposed to assign pairs of you an atom to write out the configuration for. I'm not going to assign you one atom. I'm going to assign you, what time is it right now? I think I'm going to assign you 2 atoms, because people are just getting that one atom cranked out in way, small periods of time, and then they're leaving the room. And so for the sake of giving you some extra practice, I'm going to give you 2. So find somebody to pair up with, and then come up to me, and I'll give you an element to draw up the configuration for.
Yeah.
All right, now give me an figure so I can pick my nose.